Hello, everybody. My name is Salvador Pineda, and I'm from the OASIS Research Group at the University of Malaga in Spain. And I'm going to present a joint work with Ricardo Fernandez Blanco and Juan Miguel Morales titled Time Adaptive Unit Commitment. So as most of you probably know, in the unit commitment problem, we have a set of generating units, a set of time periods, and usually, in the simple case, on known electricity demand. And then what we have to determine is the on-off status of generating units. This is a binary variable, and the power dispatch of the same of the units. Mathematically, the unit commitment problem is formulated as a mixed integer programming problem. This is just a very generic formulation. And the problem with the unit commitment problem is that it's computationally very expensive, especially if you increase a lot the number of generating units or the number of time periods. So traditionally, this problem has been solved considering 24 hourly time periods, just to reduce the time resolution. So here we, for example, have the net demand in California in the 2019 with a 14% of renewable penetration. And as you can see, considering hourly time periods, we are able to adapt fairly well to the net demand. And however, if renewable penetration increases, as this is one day in the same system in 2018 with 26% of renewable penetration, then this conventional hourly unit commitment is not that good, and we here are not able to follow very well the net demand. Indeed, the FERC Order 764 states that hourly transmission scheduling are maybe not enough to manage system flexibility. So some people are saying, well, we can reduce the time resolution maybe to 15 minutes. This is the same net demand in a 15-minute resolution, and of course you can adapt much better to the net demand. And here in this increase in net demand, we are able to follow more closely this steep variation. However, the problem is that, well, these are just some references on works reducing the time resolution for the unit commitment problem to different time steps. And all of them have in common that they are able to reduce the operating cost, but at the expense of increasing computational time. So what we are proposing in this work is, what if we still use the 24 time period, but instead of hourly resolution, we can change the duration of these 24 time steps. For example, here, during the night from 2 a.m. to 5 a.m., the net demand didn't change much. Then maybe we can have here just a single time period of 3-hour duration. And also down here, like in the middle of the day, there is also nothing much is happening. Then we can also have like one time period of maybe 3.5 hours. But then when the sunset is approaching and demand is increasing, and we have this very steep increase in net demand, then we can have a finer time resolution. We call this method time adaptive unit commitment. So the research question we have is, can we determine this the duration of these 24 time periods to make a more efficient use of system flexibility without increasing the computational time of the unit commitment problem? To answer, so this method, the way it works is quite intuitive, I think. So let's say we have the original data. This can be, for example, net demand in a 5-minute resolution. Then what we do is to compute the distance between each pair of adjacent time periods. So for example, between this time period and this time period, the distance is 9, which means that a lot of things has changed. But between these two, the distance is only 2, so not the change was not as important. Then what we do is to find the closest, the lowest distance. This is the lowest distance between these two time periods, and then what we do is to merge them, and we compute the average net demand, for example. And then we repeat these 2 steps until we just reach the final number of clusters we want. So what we do is to compare the conventional hourly unit commitment, where you just have 24 hourly time steps, and then the time adaptive unit commitment, where you can just have, you also have 24 time period, but of different duration. So we start with the original data in maybe 5-minute resolution. Then we solve the conventional hourly unit commitment. And what we do is to fix the commitment and dispatch of base unit. These are the slow units, and also the commitment of the medium units. And then we solve our real-time unit commitment, in which we consider the original data. And then we do the same, but with our time adaptive approach. And then we compare these costs of the two approaches and see what's happened. We have tried in a case study with 13 generating units. We took the demand from Spain in 2017. We also used the wind and solar capacity factor from Spain. We have different renewable penetrations. We consider all technical constraints of generating units, and then we had 3 different generating portfolios. So in the normal flex, we have 3 base units, 3 medium units, and 7 peak units. For the high flex, we don't have any base, so we move the base to here. We consider all of them are medium. And in the low flex, we mainly have base units, and the peak units are the same in all cases. And these are the cost savings between these 2 methods, the conventional hourly and the time adaptive, for the normal flex, high flex, and low flex portfolios, for different penetration of renewables. So in the 3 first rows, we have 20% renewable, but it can be 10 of wind, 10 or solar, or only wind, only solar. And the same here, but the renewable penetration has increased to 60%. So there are several interesting things about these results. First, this is quite obvious, I think. If you have more renewables, the advantages of the method we propose are more relevant. Why? Because if you have renewables, the net demand is going to change more rapidly. And then that's where our method is better at approximating these rapid changes with a finer time resolution. Then if you have more solar, you also, our method outperforms the traditional methods. And why? Because this solar power generation is anti-correlated with demand. So when solar power generation decreases, the demand does at the sunset, demand starts to increase, and then you have a very steep ramp. And that's where we can adapt a bit better to use our generating flexibility. And finally, if you have a very flexible system, then you don't really care about using one method or the other, and the difference are very small. But if your flexibility is not that high, then you should worry a little bit more about how you represent your time resolution. And this is just a summary of the talk. So we have proven that the conventional hourly unit commitment is at least questionable if you have a high penetration of renewables. If you reduce the time resolution to 15 minutes, you reduce operating costs because you make a better use of system flexibility, but you increase computational time. However, with our method, you can take some of these cost savings without increasing computational times. And these cost savings are going to increase with renewable and solar penetration and decrease with generation flexibility. So thank you very much for your attention. This is the details about the papers we published in 2019. And if you have any questions, I'll be happy to answer them in the Q&A part of the session. Thank you.